Okay, good morning everyone. So today we try to finish off all the materials and then we will review on the exam, on the final exam. So remember last week, sorry, not last week, I think Wednesday, we was talking about the AM methods, Adams-Moulton methods. So Adams-Moulton method is, like roughly you just like look up from the point Tn plus 1. So suppose you have the function f of t and y, yeah? And then, so this one is your Tn plus 1. So suppose your function, so this one Tn and Tn minus 1 and so on, so up to here. So this one is Tn minus r plus 1. Okay, so your function f look like this. So your function f, so this is function f, and then you just make a polynomial. Okay, so you construct a polynomial. So this is a polynomial p. Okay, so the polynomial p will agree with f on Tn plus 1 down to Tn minus r plus 1. Okay, so remember in the AB methods, you start from Tn and you go down. You go back to Tn minus r, right? But here in the AM method, you start from Tn plus 1 and then you go down to Tn minus r plus 1. Yeah. So the same ideas, just the different starting point. Okay, so just different starting point. And the consequence is you will have a different formula. Okay, so you have a different formula. So like before, like you have to construct the polynomial. So p will be of the form sum of f of t n minus j and yn minus j l n minus j, yeah? So this is your p, okay? And you replace you replace yn plus 1 instead of yn plus integral of f t y dt from Tn plus 1, from Tn to Tn plus 1, yeah, by this polynomial, right? So yn plus integral of p dt, Tn plus 1, okay? And, this one will be yn plus integral of this sum, so j run from minus 1 to r minus 1. So it will be sum of f of Tn minus j, yn minus j, ln minus j, integral from Tn to Tn plus 1, right? And then you pull out the sum, yeah, and you distribute the integral inside, so it will be the sum of j from minus 1 to r minus 1, Tn minus j, yn minus j, sum of, the integral from Tn plus 1 and minus j. So exactly like before, just the starting point and the end points are different. So exactly the process like you did for AB method. So IM method, you just you just start from, so j start from -1, yeah? And then you see this number, this bj, is just this integral. This integral become bj, okay? And so this one will become bj. And we just skip the detailed calculation because it will be very similar to the AB method, the same techniques. But you know, this one gives you the AM methods. Okay? So the only difference, the only key difference you have to look at is AM methods is the implicit methods. Yeah? So implicit method, because when you put j equal -1, then this one becomes tn plus 1, yn plus 1. So yn plus 1 on the left and on the right. So it's the implicit method. Yeah? So now, you know, I mean, by evaluating this coefficient for different cases, you know, suppose you put r equal 1, then, you know, you can have this method. And r equal 2, you have those numbers, those magic numbers, and r equal 3 and so on. So now, if you look at the AM2, so if you look at this one, so this one is a familiar formula. So what is this one? AM2. We've seen this before. Huh? We've seen this formula before. So AM2, I mean, if you look carefully, yeah. So AM2 is, you have the integral here. So this one is Tn, this one is Tn plus 1, yeah. And your function look like this, okay. Then yn plus 1 is yn plus integral of f ty dt from Tn to Tn plus 1, yeah. And then you approximate by the area of the trapezoid trapezium that goes from here to here. Then it will become yn plus h over 2. Well, h is this gap, yeah, this step, yeah, f of Tn plus f of Tn plus 1. Okay, so this one is just a trapezoidal method. We've seen it before, okay, and it coincides with AM2. So AM2 is just a generalization of the idea of the trapezoidal rules. Okay, because, you know, I mean, if you approximate this one by a trapezium, then you get this method. But if you approximate by something better, right, by a curve instead of a straight line, then you get a better approximation. So that is AM3 and AM4 and so on. Okay? And so I think last time we did this calculation already, yeah? So last time we did this tedious calculation and we showed that AM2, the order of convergence can be 2 or h squared. Okay, so we did the calculation for those Taylor expansion, and then, you know, after you plug it in the numbers, cancel out everything, and you just got order h squared. So now, you know, the AM2 is an implicit method, but we show that sometimes the implicit method can be converted to explicit method when you have a special case of the function f like this. When f is a linear in y, yeah, then you can solve for yn plus 1. For example, this one AM2, this is a typo, yeah. So you can solve that like this. So now, you know, like sometimes we don't want to solve a nonlinear equation every time we see an implicit method. So because you see, like if you do the project, you know, for the implicit Runge-Kutta method, every time you solve by fsolve, it slows down the whole program. And people overcome with what they call a predictor-corrector method. So they use a combination of explicit and implicit method of the same order. Okay? And so, and they call it predictor corrector methods. So for example, you know, like suppose this is the formula for AM2, right? So AM2, you know, I mean, if you put yn plus 1 here in original AM2, then this one is yn plus 1. Okay, but then you have to solve a nonlinear equation. Yeah, but you don't want to do that. So now you make a guess. You make a guess from an explicit method. What is AB2? So AB2 is Adams-Moulton method order 2. So you make a guess. Yeah, so your guess, you know, is from this formula. So this one is a formula for AB2. And you see this formula is explicit, right? Because on the left, you have yn plus 1. On the right, you just have yn and yn minus 1. Yeah? So then you make a prediction, Pn plus 1. Yeah? So we call it a predictor. And then you put this predictor into here. Okay? Then you get yn plus 1. So, you know, I mean, you don't solve it exactly, but somehow you just put in one very good approximation for yn plus 1, you know, and then you solve it. And then we use two formulas at the same time. Predictor has become predictor corrector methods. And you see, you can see that, you know, the two formulas give you the same order of conversion, order 2. Yeah? So you can carry out the same ideas for order 4. Okay, so then you have a predictor corrector method for order 4, so PC4. So PC4, you know, I mean, if you look at this one is just from the Adams-Moulton method order 4, right? So this one gives you the Pn plus 1 explicitly, because on the right everything is yn minus 1, minus 2, minus 3, and so on. Yeah? But everything is given explicitly, then you can compute the predictor. Then after that, you put in the implicit method. You see, you don't have to solve a nonlinear equation. Just put in this predictor. Okay? And this one comes from the formula just from AM4, but you replace yn plus 1 by Pn plus 1 here. Yeah? So we are not going to derive the order of conversion of AB4 and AM4, but it can be shown that, you know, by using a lot of calculation with Taylor expansion, you know, the order of conversion of AB4 will be order 4, yeah, h to the 4th, and AM4 will be h to the 4th, yeah. So then the same order of conversion will be applied for PC4. So now, so what is the difference between PC4 and Runge-Kutta method of order 4? So Runge-Kutta method of order 4 gives you 4th order conversion, right? You've seen it in the project, yeah? But then, you know, I mean, so if we compare the two methods, so for Runge-Kutta method of order 4, you have to evaluate the function at four points. Okay, at xi1, xi2, xi3, xi4. Yeah? But suppose you use PC4, then you have to compute only two evaluation at yn and Pn plus 1. Well, given that you have, you know, stored those three values. So if your function is very complicated, yeah, so it take 1 day to compute the whole function. Who knows? Your function can be composition of all the function of other function, you know, come from different engineered application. Then maybe, you know, Runge-Kutta method will take longer than the PC4. Okay. However, for PC4, then you have to compute those 3 steps. I mean, those three previous values. Right. So this is some advantage and disadvantages. So which method you choose depends on your application. So we cannot say. Yeah, to give you the same order of conversion, But in some application, maybe you prefer this PC4, and sometimes you prefer RK4. Yeah, but it's very popular. Okay, in engineering application, they use RK4 and PC4 a lot because auto conversion 4 give you a very fast conversion. Yeah, and the computation is not complicated because if you use auto 2, maybe you don't get to the small errors quickly, right? And if you give like higher conversion RK6, then the formula is more complicated, much more complicated. So maybe RK4 is sometime in the middle, so people choose RK4 a lot. So this one is, so you look at an example of the ODE like this, and so we can have like, suppose we compare 3 methods, yeah? So AB4, PC4, predictor correctors methods, and explicit run cutter method out of 4, okay? And we run it, and you can see that, so this one is the numerical solution, yeah, and this is exact solution, because in this case we know the exact solution. And you see they are comparable. Well, actually, AB4 is not as good at run cutter method, right? Run cutter method and PC4 seem to be more accurate than AB4, yeah? So when you just run from T from 0 to 1. But anyway, they still give you the same order of conversion, right? So this one, you can compute the order of conversion, based on the errors table. So this one gives you order around 4, yeah? So give you the order of conversion. Okay. And so this one is just like, another illustration of PC2 method. Suppose you use PC2 and, the starting point, you just use run scatter method, explicit run scatter method to compute the initial 2 values. And then you run PC2, okay? So now we move to the next topic is, you see, we've seen like a lot of methods, but only for one ODEs, yeah? But in the project, like you see that we can have a system of ODEs, yeah? So, in your project, you consider a system of 3 ODEs at the same time. But in general, you can have, like P or any ODEs if you wish, right? And it can be written like this. So the system, so on the left, you have only derivative with respect to T, okay, first order, yeah? So, and the second, on the right-hand side, you just have no derivatives, okay? And so this one is like, you've seen it for the project, for the Lorentz system, you have y1, y2, y3, yeah, for x, y, and z. And F1 is your first equation, F2 second and third equation. And you have some initial condition, yeah, for time equals 0, then you have those values. So if you want to compress the notation, then you can write the vector y, yeah, the bone face y, is the column vectors of P components. And capital F, is a vector function, so receiver vectors. Input is a vector, output is another vectors, okay? And then you compress the notation into just this one. So dy over dt, y is a vector. And F here, bone face, is a vector as well. So input is a vector, output is a vector. Okay, so you've seen it in the project, right? So just this one is just a generalization. So where do we see this type of example? So one example was given in the project. We have a system of ODE, but sometimes another application is when you have a higher order equations. suppose you have an order 2 ODE, which means that you have a second derivatives on the left hand side, then you can convert it into a system of first order ODE by this trick. So maybe let me give you an example. So some example like this. So example is, suppose you have two bodies problems, or two bodies that are attracted to each other. Yeah. So this one is just a Newton method. Sorry, not Newton method. Newton law. Okay. So the acceleration. Remember Newton law, second Newton law. So F equal ma. The force equal the mass times the acceleration. Right. So this one is acceleration. Yeah. We equal the force. So this one is like you have a electric force that like attract the two objects, and the force will be like follow this formula. Yeah. So R is just a distance between the two objects. Okay, and minus x. And secondly, you have the same formula applied for the second object. Yeah. So the acceleration is the second derivative with respect to x. So that's why you have this ODE. Okay. And so this one is the second equation for the second object. And initially, maybe you can say that at time equals 0, then x is very close to the second object is very close to 1. Yeah. Well, epsilon is something very small. Yeah. So very close to 1. The first object is very close to 0. Okay. So, and the initial velocity of the first object is 0. So you don't move the first object, but the second object, well, it's a small velocity. Okay. You just hit it a little bit, and then the motion of the two objects will follow this system. So this system of ODE just comes from second law of Newton. So you see the name of Newton everywhere. See Newton method, and now Newton law, the second law of Newton. Yeah. So anyone remember first law of Newton? Huh? Inertia. Yeah. And what does it say? No, object. So the third one? No, the third one is the reaction and action. Action and reaction is the third one. But the first one, I think either zero velocity or moving at a constant velocity. Anyway, anyway, I'm not very good in physics, okay? But I just know that this one comes from the second law of Newton, okay? Just F equal ma, the force equal the mass times acceleration, okay? But now, so we have this system of the second order, two equations, right? But each of them is second order. And now, because MATLAB cannot solve, second order ODE, so you have to convert it into a system of first order. So the trick is, you do like this. So you maybe you label, maybe you come up with a new variable called z1, yeah. So z1 equal x, okay, and z2 equal x prime, yeah. And so now, when you have z1 equal x, z2 equals x prime, then what is z1 prime? So z1 prime will be equal x prime, so it will be equal z2, right? And then what is z2 prime? Well, z2 prime will equal x double prime, but x double prime by this equation will be minus x over r cubed, right? So minus x over r cubed will be minus z1 over r cubed, yeah? And then you do the same for y. So now we have z3 equal y, and then Z4 equal y prime. Yeah? Then Z3 prime will equal Z with Z4, yeah? The same trick, yeah? And then Z4 prime will equal Y double prime. And Y double prime, according to this equation, is minus Y over R cubed, yeah? So minus Z3 over R cubed. So now you combine all the equations. So you have Z1 prime equals Z2, right? And then Z2 prime equal minus Z1 over R cubed, yeah? And then Z3 prime is Z4. And then Z4 prime equal minus Z3 over R cubed. So what is R? So R is just, so R square is just X square plus Y square. But in terms of Z, it's just Z1 square plus Z3 square. Okay? So now you see that you have a system, right, of first order ODE. And so on the left, you have only first order. You have only first order like this. On the right, there is no derivatives. Okay? So that is of this form. So in the past exam papers, there's a few questions like this. So you are given a system of, no, not a system, but an equation of order 2, or ODF order 2. Then you are asked to convert it into a system of, first order ODE. And that is the trick how you do it. So it's rather simple. But now, don't forget the initial condition. Okay? So your initial condition in this case will be, so Z0, so now with Z, the vector Z equals Z1, Z2, Z3, Z4, right? And then Z0 will be Z10, well, it's just X0, Z20, X prime 0, and Y0, Y prime 0. So X0 just equal, in our case, equal 0. No, 1 minus epsilon, yeah? And then this one is 0, and this one is 0, and this one is square root 1 plus epsilon, 1 minus epsilon, okay? So do not forget the initial condition, because without the initial condition, you cannot solve it numerically. Okay? So you can. Okay, so now the last topic is about stiff ODE. So now, we've seen like explicit method and implicit methods. And you see that, for explicit method, you can evaluate yn plus 1 easily. And for implicit method, you have to solve a nonlinear system. So now why bother? Why bother to have an implicit method? So why you just want to make life difficult? Why you make life difficult by considering implicit method? Huh? Yes, so that is the reason here. So the stiff ODE is the reason why we have to consider question. Okay. So that the reason we have to consider implicit method is because of stiff ODEs. Okay. So now you consider this very simple ODE. So y prime equal minus 30y. Yeah. So now you can solve it to get the exact solution. Okay, so now, so by calculus, okay, you can check y prime minus 30y, y0 is 1/3. Yeah. So, I mean, if you remember your calculus, then this one just y prime over y equal minus 30, and then you just integral with respect to dt here, and then this one gives you logarithm of y equal minus 30t, plus some constant, and then this one gives you y equal a constant c0 e to the minus 30t, right? And then y0 is c0 e to the 0, which is c0 equal 1/3. So therefore c0 has to be 1/3, so y is just 1/3 e to the minus 30t. Okay, so that is the exact solution. In this case, we know the exact solution. And now I'm going to use different numerical method to solve this ODE. But first we notice that when t go to infinity, then this one e to the minus infinity just equals 0, right? So if we have a numerical method yn, then you expect that your numerical methods, your numerical solution has to go to 0 as well. Yeah, otherwise it's a contradiction, right? So now we use like 5 different methods. So we use Euler's method, implicit Euler's method, Ron's-Kutta method order 4, Adams-Moulton method order 4, predictor-corrector method order 4. Okay? And we play around with the different step sizes and see what happens. Okay? So this is the Euler method. So now maybe let me zoom the pictures a bit bigger, yeah. So now you can see that exact solution should go down to 0, yeah. So the exact solution go down to 0 like this. So Euler method for h equals 0.05, so it oscillates a bit, then go to 0. So it's good, no problem. And now I increase the step size a little bit, so it's 0.05. So this one 0.06. Okay. Now the solution starts to oscillate. Yeah. So you see that Euler method. I mean, maybe you have seen it in the project. When you put h is a little bit big, like put h is 1, then you don't see any good solution. You see the solution could go to infinity, actually, yeah? You see, it oscillates a lot. So it's like between, I think, minus 0.3 to plus 0.3 oscillates. And while the exact solution just go down to 0, yeah? And now you increase the step size a bit more. So this one, h is 0.08, not very big. And you see, it starts to close up a bit. So see, when time equals 2, start to fluctuate from minus 1,000 to plus 1,000. Yeah? And when you just put h is 0.1, it starts to close up like 10 to the 5. So it's like 100,000. Okay? So this is Euler method. And now, okay, so I'm going to change to another method. So this is my Ron's-Kutta method order 4. So Ron's-Kutta method order 4. Okay? Exact solution still going down to 0. Yeah? But numerical solution. So you start with h equals 0.06. Looks pretty good. And now when you put h equals 0.1, start to close up to 200. Okay? And when h is 0.1, 3333 close up to a billion. Okay? Only time equals 2. Yeah? So the solution shoot up to 2 billion already. Okay? And you do the same for AB4 method, Adams-Moulton method. And you can see the same behavior, when h is 0.02. For h is 0.01, it's okay, go down to 0. But when you increase to 0.02, close up to 10 to the 18. you know, like, I don't know how many billions is, maybe, I don't know, 10 to the 18 is quite a lot. So start to close up. Yeah. And PC4, predictor corrector methods. So this is pretty good, but you know, still go to plus or minus 40 when h is 0.05. Yeah, so start to close up. Yeah. And now, how about trapezoidal method? So trapezoidal method, remember trapezoidal method is an implicit method. Yeah. So it go down 0 nicely. So h is 0.1. Okay. 0.13 still go down to 0. Even 0.25 still go down to 0. Yeah. So see, implicit method start to show the advantage. I mean, 0.2 is pretty big for the previous case. 0.2, you see that it blows up to 10 to the 18. Yeah, but here, you know, it's go down to 0 nicely. Yeah, and so now why the explicit method doesn't work? So why the explicit Euler method doesn't work? So we have to look at the formula. Okay, so now we have to look at the formula. So what is the formula for explicit Euler method? So if you remember in this equation, so you have y prime equal minus 30y, right? Okay, so Euler method, so explicit Euler method, so explicit Euler's method, then yn plus 1 is yn plus h f tn yn, right? So this is Euler method. You saw it before, right? So now what is f? So in our case, f is just minus 30y. So minus 30yn. Okay? And you plug it in. So you plug it in f, then you get this formula. So you got 1 minus 30h yn. So very simple formula, right? And now you can do it again iteratively, you know. So yn will be 1 minus 30h yn minus 1. Yeah? And so on. So it will be 1 minus 30h, 1 minus 30h, 1 minus 30h, yn minus 2. And so on. Yeah? So dot, 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 dot. So you can go back to y0. So now make sure what is the correct power here. So y0. Yeah? So what is the correct power? Is it n or n plus 1? Is it n or n plus 1? Huh? N plus 1, yeah? Because, you know, the power here plus the index here is always n plus 1. So power 1 plus n is n plus 1. Power 2 plus n plus 1 plus n minus 1 is n plus 1. Power 3, n minus 2. So the sum has to add up to n plus 1. So here is 0. So to n plus 1. Okay? So y0 is given. So you know y0 is 1/3. Yeah? So this one will be, you know, a constant. So we don't have to worry. So now we have to look at this one. So when n go to infinity, so what is the limit? So when n go to infinity, what is the limit of this factor? Yes, so it depends on how big h is. Yeah. So, but if you want limit of yn plus 1 when n go to infinity, go to 0. Yeah. So maybe it's not if, but if you want. So this one is you want. Yeah. Okay. So you want because the exact solution go to 0. Yeah. So then you have to force. Then we have to force 1 minus 30h in absolute value has to be less than 1. Right? In absolute value. Otherwise, when you just raise to the power n, it blows up. Yeah? So we solve this inequality. So this one just means that 1 minus 30h is between minus 1 and plus 1. Okay? So I solve it. So I got minus 30h here. 0, yeah. So I just take 1 away, yeah. So and this one is minus 2, yeah. Okay. So minus 30h is always less than 0 because h is positive. So this one is okay. So what I want is just 2 bigger than 30h. Yeah. Or h will be smaller than 1 over 15. Okay. So 1 over 15 is the 1 over 15 is the minimal step size. Sorry, not the minimal, but the maximal step size to make the numerical solution doesn't close up. Yeah? So you see, you have the problem with the step size. You cannot make it arbitrarily big. Yeah, so you saw it. So here, if I increase the step size, so in this case, yeah, so this is Euler method. So if 0.1, so 0.1 doesn't satisfy this one. Yeah, so this one is not valid anymore. Okay. Yeah, so this one is just exactly what I just said. Yeah, so you have to. So this is a typo. This one should be n plus 1, yeah, not n. No, 1. No. I think it's correct. So in here, because I start n plus 1, but here I start n. Okay? So then the power when you sum up is n. So this one n is correct. Yeah? The power is correct because here, in our case, it's yn plus 1. So that's why we have n plus 1 here. Yeah, but here is yn. See, in our case, we have yn plus 1 here. So that's still correct, yeah? And now, you know, I mean, you have to solve this, and h has to be less than 1 over 15. So now how about trapezoidal method? So trapezoidal method. So we look at the formula for trapezoidal method. Okay, so similarly, so now if you have a trapezoidal method, you have yn plus 1 will equal yn plus h over 2 f tn yn plus f of tn plus 1 yn plus 1. Right? And in our case, you know, f is minus 30 yn. So you got minus 30 yn here, and this one minus 30 yn plus 1. Right? So now you can rearrange it. So you make yn plus 1 to the left. So you have yn plus 1 plus h over 15 yn plus 1 equal yn minus 30 or minus h yn over 50 or 15, yeah. Okay. So this one is 1 plus h over 15 yn plus 1, and this one is 1 minus h over 15 yn. Right? And so this one is, you know, like 15 plus h, yn plus 1, 15 minus h, 15 yn. So yn plus 1 will be 15 minus h, 15 plus h, yn. Okay? So you're solving the equation. Okay? Easily. And then, you know, you do it iteratively. So by induction, yeah? So this one will be 15 minus h over 15 plus h, time 15 minus h over 15 plus h, yn minus 1, and so on, yeah? Okay? And when you stop at y0, then you got 15 minus h over 15 plus h, y0 to some power. So the power should be n plus 1, yeah? So n plus 1. Okay? So now what is the limit when n goes to infinity? So what is the limit of y plus 1? 0. Yeah? Why is that? Because h is positive, so 15 minus h is always smaller than 15 plus h. Okay? So see, in this case, it doesn't matter what h you have to put in. So limit of yn plus 1 is always equal 0, because 15 minus h over 15 plus h is always less than 1 for positive h. Step size has to be positive, right? So that is why implicit method is stable in this example. Okay, so this is the calculation again, yeah? So I just did it explicitly here. Okay, so you have 1 minus 15h. Why I have a different my calculation here is wrong, yeah? So this one should be 15 over 15, yeah? So because 30 divided by 2. So sorry, it should be 15. So the slide is correct, yeah? So this one should be, so I haven't got my coffee. So this one should be 15, sorry. So this one should be 15. This one should be 15, yeah? Because 30 divided by 2. Yeah, so this one should be 15, 115, and then you have 15h plus 1. Anyway, you got the idea, right? So 15h plus 1, yeah? So 1 plus 15h, and this one is 1 minus 15h. And then similarly, one is 15h over 1 plus 15h. So you got the idea, right? So now, so this one has to be one minus 15h, 1 plus 15h to the n plus 1. Okay? But still, I mean, you still have this one less than 1, yeah? So you still have 1 minus 15h, 1 plus 15h is less than 1. Okay, but anyway, so the idea is still correct, only the calculation. So remember to drink coffee before your exam, okay? Your exam, is it in the morning or afternoon? Okay. So. Anyway, so you see, you can see that the implicit method in this case always stable. So you see, that is an example of a stiff equation. So stiff equation, I mean, so far people haven't agreed what is the general definition of a stiff equation. But the general idea is you know, like if you have to use a very, very small step size in order to have a stable solution, then it becomes stiff. And you see, if you have a small step size, it means that it takes longer to loop over all the iteration, right? So you don't want that. Question? It is implicit. Yeah, it's equivalent to AM2. Yes. It is, you mean it equivalent, so is it implicit Euler method? No. No. The two formula are different. So implicit Euler method look like this. So implicit Euler method look like this. So yn plus 1 is yn plus hf tn plus 1 yn plus 1. So this one is implicit Euler method. Which one? Sorry. Okay. So this one is a typo. This one should be. This one should be. This one should be trapezoidal method. I think it's a typo. Yeah. So this one, because this is a formula for implicit Euler method. Okay. So this one is trapezoidal method. So I will fix it. So this one. Okay, so let's see, what did I use in the beginning, yeah? So, see here in the picture is correct, yeah? So it's a trapezoidal method. But let me go back to the beginning. So this is explicit Euler method, yeah? So explicit, so this one implicit here, see? So implicit is this one. So you have y1 here and y1 here. See, so this is implicit Euler method. So this is the formula. Okay? So there's a typo in that slide. I will fix it. So there's a few typos. So it's very good. But this is the implicit Euler method. Yeah, you have only the right ends. Okay? For the trapezoidal rule, then you have h over 2 and f the n yn plus f tn plus 1 yn plus 1. Yeah. Okay, I will fix the typo. Yeah, just the name. But you see the caption here is correct. Yeah, the caption here is trapezoidal method. Okay, so now we go back to stiff equation. So stiff equation is, you know, when you have to. Oh, sorry, should we take a break for 5 minutes? Yeah, take a break for 5 minutes. Yeah. So we start again at 11:08. Yeah. Okay. Question? Yeah. No. See, I said that you don't have to remember anything. But actually, maybe you have to remember Taylor expansion because we use it a million times. So I'm not going to give you the formula for Taylor expansion. Yeah. But all the other formulas will be given in the exam. If you look at the past exam papers, all the formula will be given. What you need to do is you need to know how to apply the general formula. to the particular case. Okay? So I don't ask you to remember any formula. Okay? But you need to understand the formula. You have to understand the format is the general formula, how you plug in. How you plug in the numbers. Okay? If you don't have to memorize any formula, except Taylor formula, because it's very popular. So I don't give you the Taylor formula and exam. You know the Taylor formula? So, I mean, like this one. So this is f of x equal f of a plus f prime a x plus x1 of a, and then f double prime a square over 2 and so on, you know, so f double prime 3 factorial x minus 1. Yeah, so I think you remember this one, everyone. So I'm not going to give this. All the formulas will be given. Okay? And you know, and integration, you have to remember your integration as well. Integral x squared, you should remember, right? I mean, I'm not going to give you a table integration. Okay? Yeah? Yeah?
One of the questions that was like, it is a good past paper. Write down polynomial degree 3px so that p a to power 130 to 0.
Yeah.
So like, because that was the first polynomial I thought of.
Yes.
It was kind of broken.
Yeah.
It was something like px equals to x minus a power 3, which is a lot messier.
Yeah.
But like the thing is, it still works, right? Because it says.
It's true. It's true.
Okay, but the problem is, why wouldn't that work for this thing? Because I know that x power 3 minus 8 that works for this. So like.
No. Then you have a different formula for this. If you use this, then you get a different formula for this. Yes.
How would you know that you've definitely chosen the correct one?
You have to try.
Oh, damn, okay. Because, like,
Okay.
the thing is,
But
it's
think of the seamless polynomial.
Seamless polynomial.
Yeah.
It's a bit complicated,
Yeah. This one is okay, but
Yeah,
you got a
okay.
different,
Different
okay.
formula, okay, so
Yeah.
it depends on the polynomial. So that's
Yeah,
kind
yeah.
of like a, see if you can deduce, like, the best polynomial kind of question.
Trial and errors, you know, a few, at least 2 iterations. Yeah.
I'm just checking my lab marks. I'm supposed to go from there.
Sorry, when is your lab?
Um,
Is it Thursday, 3 o'clock?
Thursday, yeah.
Yeah, the last one we haven't
Oh,
done last year. Michael is still a bit working on it.
Oh, okay, cool.
So he got maybe half of the class done.
Yeah. Same with the lab submissions as well.
Yeah, last edition is
Yeah.
not done as well.
Okay, no worries.
But you see, if your lab is Wednesday and Thursday 1, then I think you got the result. Thursday 2, still wait. Maybe until this week.
Okay.
I will ask Michael from him in the back and ask him to finish. Okay, no problem. Yeah? No, not X and Y. This one is T and Y. This one T. And this one is Y. Yeah. So Y is a function of T. Okay? So T go to infinity, go down. Okay? Okay, so we go back to the lectures, yeah? So okay, so the plan is we should get everything done today, and then next week we'll review on the exam. Okay, so try to finish every materials today, and the last 2 lectures we will focus on the final. So stiff equation. So go back to stiff equation. So the common stiff equation is y prime equal lambda y plus some function g. Okay, so you saw the example y prime equal minus 30y already, and g just equals 0. But in general, it could be any lambda, and lambda can be a complex number with a negative real part, very big negative real part. And it could be in the form of a system, okay? So it could be in the form of a system as well. And in the system, then A become a matrix, okay? So if you have a matrix, then we have to say something about the matrix. And the way we can say is based on the eigenvalues. So if you have, like at least one eigenvalues would have a very negative real part, right? Then it's stiff. So again, this one is not very rigorous, okay? It's just a hand waving, but it gives you like rough idea when you can see a stiff ODE, yeah? So when you have a very large negative real part for lambda, or when you have a very large negative real part for the eigenvalue, when you have a system, then very likely that we have a stiff ODE. So you have to use a very small step size, okay? And in engineering, you will see that in many cases, you have a stiff system, and you have a system of ODEs, not a single ODE. And then, you could check the Jacobian as well, right? So if the Jacobian, remember the Jacobian, in the Newton method of 2 or 3 variables or n variables, you can check the Jacobian. And if the Jacobian has a negative real parts, along with all the magnitude, then it's very likely that you have a stiff system, okay? So now we go back to the simple ODE, just a test ODE. When you have y prime equal lambda, lambda could be a complex number, yeah? Then we just plug it in, the method, okay, and see whether you have a stiff equation. So then if you plug in a system, if you plug in a method, then eventually, you have a form. So remember, we have a form like this, yeah. So yn plus 1 is some polynomial times y0, okay? Or you can have yn plus 1, okay, equals some polynomial times y0, yeah? So in general, you can have any function, a function q, yeah, which depends on h and lambda. So in previous case, lambda equal 15. So you can see that lambda come up here. So lambda equal 15. And h, yeah, so h here. So in general, it could be, any function q. And the function q will depend on the method. So this one is for trapezoidal methods, and this one is for explicit Euler method, right? So q will be different for each method. And so now it's very clear that if, the absolute value of q of h less than 1, then, your method is stable, okay? And now when the method is stable, well, so now suppose I label this to be z, okay? Z is h lambda, yeah? Then because remember lambda could be a complex number, so h lambda is a complex number, so I just put a z here. And if, that number gives me the magnitude less than 1, okay, then I call that z lie inside a stability region of the method. So in a sense that, okay, if you define this region in the complex plane, yeah, so you define the region in the complex plane when you have the absolute of QZ less than 1, then inside that region, you know, you have a stable method, and we call it a region of absolute stability. So you see, this region will be different for different methods, yeah? Because here you fix the ODE, but you vary the methods, okay? And you vary the step size, yeah? So because lambda is fixed, yeah, you vary h. So then, you know, I mean, different h will give you different z, and then you have whether stable or not, and then give rise to the definition of the region of stability. So now, suppose that, you know, your stability region contain on the half plane of the complex number, then we call it the method is astable. Again, so this one is just a definition. You know, people work on it and they say that, okay, I should come up with a name. And maybe they don't have a better name, so they just should astable. Okay? But, you know, 100 years later, maybe they will change the name, you know. Might have some name of the person here, but right now the person is still alive, so they just say that, okay, I just name it astable. Okay? Because he doesn't have any better name. And astable just means that the half plane, entire half plane of the complex plane is inside your region of absolute stability. Okay? And here, so now we go back to the explicit Euler method. So remember explicit Euler method. So this is your Q, yeah? So QZ is this one. So Z is your so why there's a minus? Okay, because a minus here, yeah? Because lambda here is minus 30. Okay? So if I put lambda is minus 30, okay, so this one is 1 plus lambda h, yeah? So lambda is minus 30. Remember, we consider y prime is lambda y, and lambda has a real part is negative. Okay, so in this case, you know, lambda is just equal minus 30, so you see, so this one is 1 plus lambda h, this one, and so this one is Q of z is just 1 plus z, yeah? And so now, you know, why I have the region of stability in this circle? Well, because now suppose I say that, so now you have QZ is 1 plus Z, yeah? And the region of stability or region of absolute stability is every complex number so that is satisfy this equation. And now, what is this region in the complex plane? So remember, if you remember your complex number, so suppose I have Z equal X plus IY, right? Yeah? Then 1 plus Z in absolute value is just 1 plus X plus IY in absolute value. And absolute value of a complex number is just the real part, 1 plus x squared plus the complex part, y squared, take the square root, right? Less than 1. Okay? And if you remember, you know, this one is just the equation of the circle. Yeah? So this one is just the equation of the circle, center at minus 1, 0. Okay? And every point that has the radius less than 1 will be in this region. So then the region will be something like this. So exactly the plot. So x is minus 1 here. And then you have your draw the circle. and everything inside is your region. Yeah, so that's exactly this region. You see, this is a -1. Yeah, so this one is x, and this one is iy. Yeah, so this is a complex plane. So just plot the region in the complex plane. So that is. So this is my sketch, and this is a nice pictures. Okay, but not the same region. And now, what is the trapezoidal method? So this is not a typo anymore, right? So is that correct? So trapezoidal method. So remember, we had this. We can come up with this formula, right? So before we had lambda is minus. Sorry, we had lambda is minus 30. Yeah? So we got minus 15 here, plus 15. So if you put general lambda, you should get this formula. Okay. And then if you put lambda equal z, sorry, if you put h lambda equals z, then qz will be this polynomial, not polynomial, a rational equation, rational function. Yeah. And now my claim is, if you plot this region, then you have the half plane, the entire half plane like this. Okay, this one is not finite but infinite, because I cannot plot infinite regions, but this one will be infinite. Okay, and why is that? Well, I mean, now we have to do some calculation. So now, suppose I have my region of stability, absolute region of stability is everything in the complex plane, and it satisfies 1 plus z over 2, 1 minus z over 2, absolute value less than 1. Okay? Then, now remember, we can write down z equal x plus iy again. Then 1 plus z over 2, 1 minus z over 2 less than 1 will be equivalent to 1 plus z over 2 less than absolute value 1 minus z over 2, right? In we just multiply because everything is positive, right? And now because z is x plus iy, so you have 1 plus x over 2 plus iy over 2, absolute value less than 1 minus x over 2 minus iy over 2, right? And then, so this one will be, absolute value in the complex number is like you take the real part, you square it, and you have the imaginary part, yeah, squared, and then take the square root, and then 1 minus x over 2 square plus y over 2 square, right? So, well, because square root, so you can square the left and the right hand side. You have 1 plus x over 2 square plus y over 2 square less than 1 minus x over 2 square y over 2 square, right? And now you can expand it out. So if I expand it out, then this one gives me 1 plus x square over 4 plus 2 times x over 2. What is x? Plus y square over 4 less than 1 plus x square over 4 minus x plus y square over 4. So now there's a lot of cancellation, right? So now the 1 here cancel, x square over 4 cancel, y square over 4 cancel. So what do you have? What do you have left? What do you have left? So you just have 2x less than 0, right? Or x less than 0. So x less than 0 is everything in the entire half plane. Yeah? You see? So by this calculation, this means that everything in the half plane of the complex plane is okay. is in this region. Okay, so that's why I have this region of stability here. And you see by the second definition, just say that it's astable. Okay, astable when you contain the whole real line, I mean the whole negative real line, so astable. So now, so this one will be more complicated. So suppose that you have an explicit Runs-Kutta method of order 4, then, you know, QZ can be written like this. It's rather complicated, yeah? So 1 plus Z squared over 2, Z cubed over 6, Z4 over 24. And this is a familiar table, so explicit Runs-Kutta method of order 4. And for implicit Runs-Kutta method of order 3, you know, QZ will be given like this, where the implicit Runs-Kutta method of order 3 given by this table. Okay? So explicit, now you have implicit, then QZ will be different. Okay? So we can show the figures for explicit Runs-Kutta method of order 4 look like this, and implicit Runs-Kutta method of order 3 look like this. Okay? So let's say we have time to do at least one thing, yeah? So maybe go back to this, see whether we can work it out why QZ is of this form, yeah? So remember, I think hopefully we still have time for one example, yeah? So now, so remember what is Runs-Kutta method of order 4? Or explicit Runs-Kutta method of order 4. So now the ODE will be y prime equal lambda y. Okay, so remember this is our test ODE. So it will be like this. And now what is the RK4? So RK4 will be well, Xi1, Xi2, Xi3, Xi4, and then yn plus 1. Yeah. So Xi1 will be yn, Xi2 will be yn plus h over 2 f of Tn Xi1, yeah, according to this table, and Xi3 will be yn plus h over 2 f of Tn plus h over 2 Xi2, yeah, by this second row. The third one will be yn plus hf Tn so this one is Xi1, Xi2, Xi3. So Xi3 will be h over 2 Xi3. Okay. Sorry, which one? But this one is 1, 2, 3. Yeah. So this one should be, yeah. So this one should be h over 2. Yeah. No. This one is C4. C4 is right here. So this one should be C3. Yeah. Okay. And this one is C4. Yeah. Okay. So that is, and but the coefficient here is 1. So it's 1. So that's why I have H here. Yeah. And now what is yn plus 1? So yn plus 1 is yn plus. So now we have to use this coefficient. So h over 6. F of Tn Xi1 plus h over 3 f of Tn plus h over 2 Xi2 plus so h over 6 h over 3 f at Tn plus h over 2 Xi3 plus h over 6 f of the n plus the last one will be h and xi 4. Okay? So this is explicit unstructured method order 4. Okay, based on this top law. So remember in the exam I give you the top law and I give you the general formula for the explicit unstructured method. In the general formula line in the lecture note, you have xi 1, xi 2 up to xi nu. Yeah, and then you just plug it in. So now we plug it in so this one is your f, so this one is your f, right? So now I have to plug it in. So now I will have, so xi 1 will be yn again, yeah? Xi 2 will be yn plus h over 2 lambda xi 1, yeah? Because this is your f, yeah? But what is xi 1? So in this case will be yn plus h over 2 lambda yn, because xi 1 is yn, okay? So this is your xi 2. So your xi 2 will be 1 plus h lambda over 2 yn, okay? Or because we have z equal h lambda, so will be 1 plus z over 2 yn. Yeah? So remember z is h lambda. Okay, so that's why you can have xi 2 like this. So far so good, right? So now xi 3. So xi 3 will be yn, yeah? Plus h over 2. And now because the right hand side doesn't depend on t, so you don't have to worry about this one. Yeah, but now you have xi 2. So you have lambda xi 2. Right? And now what is my xi 2? My xi 2 is here. So I put it in here. So then I have, plug it in here. So I have yn plus, so h lambda is just z over 2, right? So I have z over 2, then xi 2. And this is my xi 2. So it will be 1 plus z over 2 yn. So remember this is my xi 2. Yeah? Okay? And so therefore I have xi 3 will be yn, right? Then 1 plus z over 2. I just multiply this, yeah? Plus z squared over 4. Okay? Got it? And now, similarly, I can have xi 4. So my xi 4 will be yn plus h lambda xi 3, yeah? Or yn plus z, yeah, because this one is z, yeah, times xi 3. So xi 3 is right here. So yn, then 1 plus z over 2 plus z squared over 4. Okay? It's a bit tedious, but I show you the process. It's not hard. I mean, just where to plug in the symbols. In the end, you just play around with the symbols. Okay? And now, if I rearrange it, I will have yn 1 plus z, yeah? So I just rearrange it. So yn is 1 here, and z yn times 1, and then z squared over 2, and z cubed over 4 for my xi 4. Okay? So far so good, yeah? And so now I have to compute what is yn plus 1. So my yn plus 1 will be, according to this formula, so will be yn plus h over 6 lambda xi 1 plus h over 3 lambda xi 2, yeah, plus h over 3 lambda xi 3 plus h over 6 lambda xi 4, right? Based on this formula, yeah. And now I just plug it in. I plug it in. So I have my xi 1, xi 2, xi 4 already. Yeah. So I just have yn plus. So because h lambda is z, okay. So I have z over 6 xi 1, okay, and xi 1 is just yn. Yeah. And then so this come here, yeah. And then for this one, I have z over 3. So remember, h lambda is z, yeah. So h over 3 xi 2. So where's my xi 2? So xi 2 is here. So 1 plus z over 2 yn. So this is my xi 2. And plus z over 3, yeah, my xi 3. So xi 3 will be here. So 1 plus z over 2 plus z square over 4 yn. So this one is my xi 3. And then the last term will be z over 6. Xi 4 will be 1 plus z square over 2 plus z cubed over 4 yn. So everything now just yn and z. Yeah? So everything now just z and yn. And now I just rearrange it. So now yn is a common term. Okay? So yn will be the common term. So it will be yn, very big bracket, as big as it can be. Yeah? And then you have 1 plus z over 6, yeah, plus z over 3, okay, plus z square over 6, okay, and plus z over 3 plus z square over 6 plus z cubed over 12 plus z over 6 plus z square over 6 plus z cubed over 12 plus z4 over 24. Yeah? Agree? Yeah, I have to move up. Yeah, so the calculation is a bit tedious, but it can be done, yeah? So after you plug it in correctly. And so now you can combine the terms. You combine the terms. So I have yn. So I have 1, yeah. So this one is 1 over 6 plus 1 over 6 is 2 over 3. So 2 over 3 plus 1 over 3 is z. Yeah. So this one is done. Okay. And how about z?
There's one more z over here.
One more z over here. So
z over 6 plus z over 6 just equals z over 3. So it's still fine.
Sorry, so z over 3. So z over 3 plus z over 6. So this one is 1 over 3, yeah? And then 1 over, okay, so this one is, yeah, so sum up to be z, yeah? So it's good. The first two terms is correct. So we are on the right track, okay? Okay, so how about z squared? So z squared you have 1 over 6, 1 over 6. So 1 over 6, so 3 over 6. So 3 over 6 is z squared over 2, so it's good. Yeah? And then the quick one. So the quick one is 1 over 12, 1 over 12, so 2 over 12. So z cubed over 6. And then the last one, there's no common term, so 24. Okay? So therefore, this is your QZ. So after you plug it in and then, yeah. So that is how I got the QZ over there. Okay? So So it's not too bad, right? I mean, as long as you do the calculation correctly. Yeah? But you see, I mean, if you don't show me the step, I mean, you said that obviously QZ equals this, and you don't get any marks. Okay? You know, you don't say so obvious. It's not so obvious. Yeah? Question? Good point. Look like a Taylor series, yeah. Because you have one yes, look like a Taylor series of exponential, right? Good point. Why is that? I don't know. Very good observation, yeah, but it looks like a Taylor expansion of e to the z, yeah. But maybe, I mean, maybe there is a reason, because remember you have this, you have this y prime, yeah. So then the solution, exact solution, is exponential of something, right? So therefore, the numerical example should approach to the exact solution. Yeah. So therefore, you know, this one is approximate of e to the z, yeah, because your exact solution is e to the z, you know, so that makes sense. So everything should go to the same correct solution, yeah. So that is one more reason, one more thing to check, you know, if you don't have a correct polynomial like this, then, you know, have to go back and check, yeah. But you see, I mean, eventually, you see everything fit together. You know, Ron-Cotta method, exponential function, ODEs, but it seems that it fit together like a piece of puzzle, you know, like it just come from different direction. But it just show you there's only one correct solution, yeah? And you see, for this implicit Ron-Cotta method, you have this rational function. So, you want to try this, or you want me to do it? So maybe if we have time, we can go back to this, yeah? So now just move to the end of the lectures, and then if we have time, we can go back to this calculation. But it can be done, okay? So it can be done. So maybe this one you know it already, yeah? So this one is like ODE 4.5. ODE 4.5, you've seen it already in your project. ODE 4.5, actually it's just a Ron-Cotta method between order 4 and order 5. And it adjusts the time step, you know, so that it can solve the ODE in the fastest way. But you have other ODE solver as well. So ODE 2.3, Ron-Cotta method, order 2 and order 3. Adams method, and this one is backward differentiation, so we don't have to worry about this, but it's ODE 4.5, stiff. So this one is specialized for stiff ODEs. And Rosenbrock method, so don't have to worry about this one. So they have a trapezoidal method as well, and backward differentiation, so don't have to worry about this one. But essentially, you know, MATLAB provide a library of ODE solvers. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and we just play around with the first one. But depends on your ODEs. You can try, you know, other solvers. And those ODE solvers now available in other languages as well. So if you use Python, you use Julia, you use Octave, you know, so then those are available as well. But you see, at least you should know how it works before you use it. Otherwise, it becomes a black box, yeah? And so this is how you solve it. So, you know, you replace the solver by the name of the ODE solver, put in the option, and put in the right-hand side. Yeah, so now by now you should know how to do this one, so I don't have to do it. Okay, so that is everything about ODE. So maybe we have a few minutes to go back to this calculation. So how do we do this one? So now for this implicit run cutter method order 3, yeah. So again, so you start with the ODE y prime equal lambda y, yeah. Then you have a top load like this. So 0 here, so 2/3 here, 1/4 minus 1/4, 1/4, 5/12, 1/4, 3/4, yeah? So this one you have xi1 will be, so xi1 will be yn plus h/4 f of Tn xi1 minus h/4 f of Tn plus 2h/3 xi2, right? And then xi2 will be yn plus h/4 f of Tn. So I use this number, yeah? xi1 plus 5/12 h f of Tn plus 2h/3 xi2, okay? And then yn plus 1 will be yn plus h/4 f of Tn xi1 3h/4 f of Tn plus 2h/3 xi2. So this is a general formula, okay, for this top load. And now you plug it in your f. So remember, this is your f. Your f is the right hand side, yeah? Then you have to plug it in. So you have xi1 will be yn plus h/4 lambda xi1 minus h/4 lambda xi2. So remember, there's no t, so we don't have to worry about t, yeah? Okay? And now, similarly, you have xi2. So xi2 will be yn plus h/4 lambda xi1 minus 5 h/12, plus, yeah, plus h/12 lambda xi2, okay? So now we look at this for a moment. So you have xi1 on the left, xi1 on the right, xi2 on the left, xi2 on the right. So it's a linear, well, it's a system, but it's linear. So actually you can solve it. Yeah, you can solve it for xi1 and xi2. So suppose I solve it. So now, maybe before I solve it, let me replace h lambda by z. Yeah? So I have, so xi1 will be yn plus z/4 xi1 minus z/4 xi2. Yeah? And then xi2 will be yn plus z/4 xi1 plus 5z/12 xi2. Right? Okay? But I can solve it, right? Because now I have 1 minus z/4 xi1 is yn minus z/4 xi2, right? I just rearrange it, and I have 1 minus 5z/12 xi2 is yn plus z/4 xi1, okay? So I can solve by substitution. Yeah, for example, so I have say this one is 1, this one is 2. Can I solve it by, yeah, maybe substitution is okay, yeah? So substitution then, so if I take 1, right, then I have xi1 will be yn minus z over 4 xi2 divided by 1 minus z over 4. Okay, then I substitute to 2. Yeah, so substitute to 2, so this one my 3 into 2, then I have 1 minus 5z over 12 xi2 equal yn plus z over 4 xi1, but now xi1 will be yn minus z over 4 xi2 over 1 minus z over 4. Right? So I can have xi2. So I have, okay, so now I just expand it. So 1 minus 5z over 12 xi2 is yn plus, so will be z over 4 over 1 minus z over 4 times yn. Yeah, so plus or minus, yeah, minus z square over 16 1 minus z over 4 xi2. Yeah, because I want to rearrange xi2 into the left hand side. Okay, so I can make it look nicer before I do something. So this one will be yn, then I multiply by 4. I just have z over 4 minus z yn, and multiply by 16. So z square over 16 minus 4z xi2. Right? And then I move it to the left. So I have 1 minus 5z over 12 plus z square over 16 minus 4z xi2 equal yn 1 plus z over 4 minus z. Okay? So it's a bit tedious, could be done. So now, so you have, so maybe we have to take the common denominators for, 16 minus 4z, okay, and maybe multiply by 12. So here then I have 12, 16 minus 4z, then minus 5z times 16 minus 4z, and plus z square times 12. Yeah? xi2 equal yn 4 minus z, 4 minus z plus z, or some cancellation, yeah? So this z and minus z goes away, okay? And so what is xi2? So if you solve for this, then you have xi2 will be equal something, right? So it will be, so 4yn. So this one can cancel, right? Because this one is 4 minus z. So 4 minus z here, if you cancel this, you cancel 4 minus z here. So you got 12 times 4 left, yeah? So it will be 48. yn divided by, no, I forgot number 4, there's a number 4 here, yeah? So time 4 divided by 12, 16 minus 4z, 5z, 16 minus 4z plus